Okay, Assalamualaikum and a very good afternoon to all. So welcome to our third class, Thermodynamics 2, KNC 2113. So our lecture today will be on lecture 3, Solution Thermodynamic Applications. Okay, the objective of our study today will be to examine the measurements of vapor liquid equilibrium VLE data from which activity coefficient correlations are derived, and also to treat mixing experiments which provide data for property changes of mixing. In particular, practical applications of the enthalpy change of mixing. Okay, this is called the heat of mixing. Okay, the liquid phase property from VLE data, so that if let's say we have a vessel here, okay, let me use my pointer first, my laser pointer, okay, right? So let's say we have a vessel here, so on the top part we have vapor, and the bottom part we have liquid, because the system here are in equilibrium, so the temperature and pressures are the same, okay, right? Okay, now for species are in the vapor mixture, we can denote it into this. Remember, this is the symbol for the solutions. Okay, cap here. This is for vapor I, YI. Okay, this is the activity coefficients. Okay, P. Okay, this, and then this is for the liquid part here. Okay, right? So if let's say the vapor is in the ideal gas form, then the phi here should be equal to 1. Okay, remember what phi is? I'm sorry, guys. The fugosity coefficient, okay, right? Because this is vapor, it's not liquid. Okay, so when phi is equal to 1, when it's ideal gas, right? So mean that the fugosity and the pressure are the same. Okay, I do apologize. Okay, phi is actually fugosity coefficient. Okay, so for the fugosity of the species in both liquid and vapor phase is equal to the partial pressure of the species in the vapor phase. Okay, right? So we can plot it, okay, right? For fugosity 1 equal to y1p and fugosity 2 for y2p. Okay, right? So this is denoted as in table 12.1 here. Okay, right? So this is our pressure here. Okay, uh, this is our pressure for pure species 2, yeah, and this is vapor pressure for pure species 1. Okay, this is x1 for liquid and this is for vapor. This is viscosity 1 and viscosity 2. Okay, this is another alarm gamma 1 and gamma 2. Okay. Okay, if we plotted it here, we can see that, so this is the plot for species 1, okay, right? Fugosity species 1. Okay, right? When it's 0, then the fugosity is 0. But when it's 1, okay, right? Pure species, then it's equivalent to the saturated pressure of species 1. Okay, fugosity 1 is equal to saturated pressure of species 1. And this for species 2. If you guys can see that this line is very close to this dash line. If you still remember, this dash line is the Lewis-Randall's rules line. Okay, so the closer is it, then it's the closer is it, then the closer following the ideal solution. Okay. Okay, right. The straight dashed line represent the Lewis-Randall rule, which express the composition dependence of the consistent fugosity in the ideal solution. Okay, right. So this is the ideal solution. Okay, Lewis-Randall's rule. Okay, right. But from this graph here, okay, right, if we plotted, okay, right, for species 1 here, the line here, we can see that as it very close to the pure species, right, the fugosity in the solution for species 1 almost follow Lewis-Randall's rule. But when it in finite dilutions here, it deviates quite a lot. Okay, right? So from this, as you read in the book, it says that for pure species, it's better to use Lewis-Randall's rules. And then for finite solution, or when the fugosity of uh, species 1 is almost 0, then towards 0, then we need to use Henry's law. Okay, that's what the slide is mentioning about. Okay, right. So this is the proof that when we're going to use the Henry's law. Okay, that this Henry's law here, we use this slope there. Okay, guys. Okay, right. So for pure species towards pure species, we use Lewis-Randall's rule, and for infinite solutions, then we use Henry's law. Okay, right. So Henry's law. Okay, this is the sum what I told you earlier. Okay, Henry's law applied to a species as it approaches infinite solution. Okay, you can see it here in a binary solution. Okay, for in methanol, it is a positive deviation. Okay, right, above the Lewis-Randall's line here. Okay, right. But for in chloroform, it's a negative deviations. Okay, right. But as both are approaching pure species, both follows Lewis-Randall's rules. Okay, right. This is uh, uh, men mentioned by Gibbs-Duhem equations. Okay, right. So for the excess Gibbs energy, we have done this earlier. We can rewrite it into this form here. Okay, right. GEE indicate excess. Okay, excess is for the solutions, and R is for the residual, is for the ideal gas. Okay, we can plot it in this form here. Okay, right. So remember, this is the pure species saturated pressure, and this is the pure species 1 saturated pressure. Okay, this is X1 and X1 and X2, lone 1. Okay, and then we can plot it. And then we can calculate GE over RT here, and then GE X1 X2 RT there. Okay, right? So we can get this result here, and then we plot it into a graph. Okay, right? Okay, for the first plot, okay, right? For the first plot, okay, this and that. Okay, right? So we got this. Okay, okay, right? So this is the saturated pressure line. Okay, right? For liquid, the saturated liquid I'm sorry, this saturated liquid line and this saturated vapor line. Okay, right? So mean at the bottom here the pressure is higher. Okay, right? Okay, I'm sorry, over here higher and over here is lower. Okay, right? But if we plotted this graph here, okay, right, this graph here, lone gamma 1 and gamma 2, okay, right? So we will get this graph here. Okay, right? So if you guys can see that, and this is for GE. GE is a curve here. Okay, this is GE line, curve like here. As you guys know that, when you plotted loan, that it will never ever touch when it's come to 0, isn't it, right? It's the same also for here. It will never touch 0. Okay, right? So we have the difficulty to determine what is the coefficients here. Okay, right? For calculation. Okay, nah? But somehow we can figure it out by using this equation here. We divide GE over X1, X2 RT. Okay, right? Then we will get this. Okay, we can get this line here, right? And if we extend this line here, then it will intersect at this axis here. Okay, when X1 equal to 0 and when X1 equal to 1. Okay, right? Okay, so what is that line actually? Okay, okay, right. So okay, I already explained it here. Okay, what is that line actually? Okay, that line is indicate, okay, right, that we can create a straight line like this. Okay, a straight line. Okay, right, straight line with this equation here. Okay, where this coefficient is that value here when it touch axis x1 equal to 0, or when it pure species 1 as pure species 2, and it is a12 when it this here. Okay, okay, right? So we can have these equations. Okay, right? So when we have this value, then for finite dilutions, or when it when it's pure species 1, then we know that how much is it. Okay, so this we can rewrite it into this form here, okay, right, with this coefficient here. Okay, right? So this will be much easier to determine ln gamma 1 and ln gamma 2. Okay, right? So it's not infinite anymore. Okay, right? So we can estimate when it's pure species. Okay, remember over here when it's pure species 2 and this is when it's pure species 1. Okay, right? So from there, okay, right, we can get this equation here. Okay, right? When x1 is 0, okay, right? 1, 2, okay, right? And this is 2, 1. Okay. Okay, right? So from there, okay, right? From the result of the experiment plus the calculation, then we can find what this coefficient here. Okay, right? So for A1, 2 over here, well, when it's pure species 2, okay, right? It's 0.32. Okay, when it's pure species 1, it's 0.198. 198. Okay, right? So we can rewrite this equation again into that simple form. Okay, right? Okay, so this is much easier. Okay, right? So it's much easier to relate x1 and x2. Okay, right. So the next one is the liquid phase properties from VLE data. Okay, data reductions. Okay, right? In the equation, concisely store the information of the data set. Indeed, the Margulis equation for ln gamma 1 and gamma 2 allow constructions of correlation original P, X1, Y1 data set. Okay, right? So from this, we know this equation earlier, okay, right? From 2.1 and this also, and then we also know this, and then we can combine it. We got this Y1 into this form here. Okay, right? Everybody know that P total pressure is the combination of the partial pressure. Right, so this is partial pressure 1, this partial pressure 2, that's the total pressure here. Okay, right? So if we combine this P or put P in any of this equation here, then okay, we put it here, then we got Y1 to here because it divide, right? We divide by that. Okay. Okay. So and again, we can got the data here for this for saturated pressure species 2, this is 1, x1, y1, and then we plot this equation here, and then we got this equation. And still again, over here, we got negative deviations, okay, right? This is saturated uh, vapor line, this is saturated liquid line. Okay, this so mean that the mixing of chlorofluoro, chloroform 1 and 1,4-dioxane, that it provide a negative deviations. Okay, still again, we still can use it, this data here, to find what is this value over here. Okay, from that value, we got the A1 is 0.72, okay, 0.7212, okay? And then this is negative 1.27 here. Okay, negative 1.27 there. Okay, right? Okay, right. So from that, we can create the equations. Okay, right? So the Gibbs theorem equation, as you can see earlier, okay, right? The Gibbs theorem equation, sometimes the 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 result is positive deviation and sometimes negative deviation. So we need to find something that to tell us the how consistent it is. Okay, this for thermodynamic, we call this as thermodynamic consistency. Okay, right? For this consistency, we can rewrite it into this form here. We use the asterisk. Okay, right? Just asterisk to test the consistency. Okay, right? So the asterisk here, we have seen this equation before. Okay, right? For equation 12.1, and then from there we just derive the delta GE over RT, can differentiate the equation to give this or this, right? And then we deduct it from the actual, okay, right? The actual excess Gibbs energy. Okay, E, remember E is the excess gives energy, we deduct that, and then we get this equation here. Or because this is the differences, okay, the residual, okay, the differences, we can denote the delta here. It's the same also for here. We can denote it as delta. Okay, right? And then as it approaches, okay, ideal solutions, okay, right? This will be 0, isn't it? Right? So delta GE, it should be the same. Okay? This should be equal to 0 because when it equal to solution. So then delta ln gamma 1 over 2 will equal to this equation here. Okay, right? Because it's almost scattered to 0. Just means that if GE over RT is equal to 0, means that it is exactly the ideal solutions. Okay, right? So it varied a bit, but normally it's just very close to it. Okay. Okay, models for excess given energies. Okay, general GFT, we can form it into this form, okay, right? For constant T, right? G, X1, X2, Xn, right? Or we can expand it into X1, X2, A plus B, X1 plus C, X2 plus, this for constant T. Okay, if you still remember that from this equation here, for ideal gas, for ideal solutions, we ignore this. Okay, what does this mean? This means that for ideal solutions, the molecules are independent. Okay, not independence mean that it does not have the influence of other molecules. But when you have B constant here, means that these gas or molecules have the influence of another molecules. Okay, the first degree. And C is the second degree. Okay, right? This first, second, and then we have another third one, which influence B, B influence A. Okay, right? So this is become more complicated. Okay, there is a third viral, a third, this first, second virals equation. Okay, right? So we can expand this and we allow x2 equal to 1 minus x1, then we can get this red list crystal expansion. I think you should remember this in lecture 1. I'm sorry, in Thermo 1, okay, for ideal gas. Okay, so this is very similar. So this is the first, second, third, okay, viral. Okay, so if A equal to B equal to C equal to 0, means that, okay, everything here will be this 0, this will be 0. Means that it is exactly ideal gas, ideal solution, right? So with GE is equal to 0, means that it is the ideal solution. Okay, if let's say B equal to C equal to 0, but not A, this is got here. So means that we got some value there. GE is not 0. So means that there's a difference between the real gas and also the ideal gas. Okay, so where A is a constant for a given temperature corresponding for this, and then we can get this value here. Okay, right? So we can get gamma 1 and gamma 2, ln gamma 1 and ln gamma 2. Okay, right? And then if let's say C is not 0, then this equation become more complex. Okay, right? So we need to have B there. I can rewrite it into this form. Okay, right? And then we can have this. And then you so on and so on. You can go for C, D, E, G. But the more coefficients you consider the effect, the more complicated will be the equation is. Okay, right? Well, in thermodynamics, the third, fourth, fifth, sixth, seventh, 100 virals, equation does not have much effect. Okay, right? So we just consider normally the first and second, or maybe third. Normally first and second. Okay, another well-known equation result from the is just, so we can do the reciprocal expressions here. Okay, inverse. Okay, right? When the inverse is very much similar like previously, but it is inverse. So we can manipulate these equations, and then we can get this equation here. Okay, GE equal this or this. Okay, and this is and then we can get ln gamma 1 and ln gamma 2. Okay, this is called the Van Laar equation. Okay, right? So you want more details, you can look for it. Okay, right? But for these classes here, we just apply what been derived. So it's not an classical thermodynamics class where you need to derive. Okay, I think this is good enough that we just use the equation and apply. Okay, local composition model. There are also some other models that can be applied for our excess Gibbs energy. Okay, right? The first one is NRTL, or non-random to liquid. Okay, this is developed by J.M. Wilson in 1964, and then another one will be UNIQUAC, okay, or universal quasi-chemical equation of Abraham-Sapkowski. Okay, and then it further developed again into UNIFAC methods. Okay, okay, for the first one, okay, NRTL, okay, non-random two liquid equations, okay, it can be written into this form here. Okay, this lambda 1 2 lambda 2 1 is very similar what we apply for the A just now, okay, so we can rewrite it into this form here, and then we will get lambda at finites. Okay, finites here, we got this equation here, and then lambda 1 and 2 must always be a positive number. Okay, okay, and then this, yeah, because you cannot have a negative ln, isn't it, right? And then ln gamma 1 and ln gamma 2 here, and then we can find G2 is this alpha tau 1 2. Okay, alpha 1 2, this is tau, is this value here, and alpha B12 B12 are particular special independent of composition. Okay, normally this we got these values from our experiments. Okay, right? So gamma 1 alpha, this equation here, gamma 2, this equation. Okay, for UNIQUAC and the UNIQUAC methods are model of greater complexity and treated in the appendix H. Okay, so you want to more detail on this, you can read, okay, how that been develops. Okay, as you can see here, we have I and J. Okay, right? So it means that we can apply this equation for more than 2 species. Okay, 3 species or 4 species. Okay, right? So it's very similar to the NRTL. Okay, so we can need to find the coefficient first. Okay, property changes of mixing. Okay, equation 11.9 and 11.2 are expression for the property of either solution. Each may be combined with the defining equations for an excess property. Okay, GE, G, okay, SE, okay, this is Gibbs energy, entropy, volume, okay, and then the enthalpy here. If you notice that this is the excess, isn't it, right? So we can write it into this form, okay? Molar solution properties, okay, right? Molar properties here. Or we can write it into this form here, and then we can denote that with delta M. Okay, right? So we can have this delta M, so will be delta G, delta S, delta V, delta H. Okay, is this following here? Okay, right? And then for ideal solutions, each excess property is 0. And for this special case, this equation becomes, okay, that for ideal solution means what? GE is 0, excess, okay, it's the same. And real and actual are the same. So GE equal to 0, this all equal to 0, right? So we got over here, delta ideal IG is equal to that. And this 0, this ideal solution, this, and that will be 0. There are both volume and enthalpy equal to 0. Okay. The equation alternative form equation that's written here, they are applied to ideal gas mixture as well as to ideal solutions. Okay, right? So we can write delta M equal to MID minus this. Okay, right? Substituting this question in for equation 2.29, okay, previously. Okay, right? We can get delta M minus delta IM equal to M delta MID. Okay, right? Because these, right, M, this is actually M minus delta, hold on, let's go back, 12.29, okay, see here, this equation here, so this is actually put it over there, become M minus delta M, okay, so M minus delta M, okay, right, okay, go to here, minus M minus delta M, so we can rewrite it into this form, and with this combination, we can find that M delta, ME, excess is equal to delta M minus delta M ideal solutions. Okay, property of mixing in experimental character assumes that we have these piston terms, can I add add what constant, okay, let read this question. An experimental mixing process for a binary system is presented schematically in figure 12.10. The two pure species, both T and P, are initially separated via partitions, withdrawal of which allowed mixing. Okay, initially they're separated, and after that it is allowed to mix. Okay. As the mixing occurs, expansion and contraction of the system is accompanied by movement of the piston so that the pressure is constant. In addition, heat is added or extracted to maintain a constant temperature. Okay, the temperature is constant. When the mixing is complete, the total volume change of the system as measured in the piston D is okay. So the change in delta V is equal to the total number of mole times the volume V minus each of this mole volume 1. Okay, right? Okay. Okay. So why we have the volume here? So why we can use enthalpy here? As you guys remember that enthalpy is what U plus PV. Okay, right? Okay, so H equal to U plus PV. Okay, right? So when this the volume change, then we have work have been done. Okay, right? So we cannot ignore the PV part. Okay, so we need to use the H. But if let's say the system has fixed volume, so there's no work have been changed. So there will be only Q equal to U. So Q also can equal to H. Can I? Or just can put it here. Q equal to H, which H is U plus PV. When volume change, that you use enthalpy U plus PV. But there is no volume change, then delta V equal to 0. So it's only U. Okay, remember that. Okay, so Q equal to delta HT total. Okay, right? So we can use this equation here, total number of mole minus the mole 1 and H2. Okay, so we got delta V is also the same. Okay, right? So and H is this. Okay, we can manipulate to that. Okay, right? Q over Ni over Nt. Okay. So thus the volume of mixing delta V and the enthalpy change of mixing delta H are found from measure quantity delta V total and Q. Because of it, the association with Q, delta H is usually called heat of mixing. Okay, heat of mixing. If you mix something, guys, right, even though it's the same temperature, sometimes the mixing will produce a bit of heat. Okay, right? Okay, right. Figure 12.2 show the experimental heat of mixing or enthalpy for ethanol water system as a function of composition for several temperature. Okay, so if you look at here, this is the excess internal enthalpy. I'm sorry, this is the excess enthalpy for the ethanol at various temperature. You can see that here the enthalpy varies. For example, at 30 degrees Celsius, okay, you can see that a very low, a very the infinite, it produce a negative. But as the enthalpy increase, as the concentration of ethanol increases, it become zero. Into pure species. But when you increase the temperature here, not much. of different from the enthalpy, but the equimolar, oh, there's a different there. Okay, right? So it behave differently at different temperature. Okay, right? What do you think? Okay, right? Well, most possibly, if you look at temperature here, because ethanol and water, okay, right? At 30 degrees Celsius, both ethanol and water are in liquid form, okay, right? And then 50 is still in liquid form, but at 70 here, okay, we already know that ethanol, uh, the boiling temperature is 78, if I'm not mistaken. So means that at 90 here, the ethanol is in gas form, right? And 110, both ethanol and water are in gaseous form. Okay, so see the properties, okay, right? The temperature does affect the properties, the excess enthalpies. Okay, property changes of mixing. Okay, so we need to look at what is the property changes of mixing. Okay, we just go here. Okay, now for pure species, at pure species 1, I'm sorry, pure species 2 and pure species 1, all of these properties are 0. Okay, this is mentioned by delta M is 0 for pure species. Okay, right? And all gives change and gives energy are negative. Okay, gives energy change of mixing delta G is always negative. Okay, why do you think, guys? Negative. Let's go back here. Why is it G is negative? Because it when it makes maybe the collision between the molecules. Okay, right? So it loses energies there. Okay, right? Okay, right? So when you make something, the molecule it collide with each other, so it causes some abrasion and lose the energy. Okay, that's my opinion. So looking at the statistic model, okay, the molecular model. Okay, and delta S is always positive. Okay, look at here. It's always positive. Okay, delta T, delta S is always positive. Why delta S is always positive? Because yes, because entropy always be generated when you do mixing, isn't it, right? That is the second law of thermodynamics. Because entropy cannot be negative. It can need to be positive because of the mixing. Okay. Okay, the heat of mixing defined by this, okay, heat of mixing, this delta H is the actual and the constituents. Or we can, for binary system, we can write it into X1, H1 plus X2, H2 plus delta H here, okay, right? Okay, right? For in terms of solute, okay, the enthalpy of mixing for solute, you can use this symbol here as a wave here, is equal to delta H over X1. 1 is the mole of uh, uh, a species in liquid form. Okay, right? Okay. And then let's say we try to mix lithium chloride with water to produce an aqueous. Okay, right? Lithium chloride. Okay, right? Okay. With this, it's found that it produces about this much energy. Okay, right? So this is the energy for heat formation for lithium chloride. Okay, right? So let's say we want to see the reaction of lithium chloride in 5 moles of water. Okay, right? So this is lithium chloride. Okay, this lithium chloride in solid form, and mix it with water. But since there's no equation here, so what we can do is that we can combine here lithium react with chloride was water. Okay, right? This is the value here to produce lithium chloride in aqueous form. Okay, right? This minus 436.805, okay, negative, right? So what is the negative? It releases the heat, okay, right? So it's a positive, then it absorbs the heat, okay, right? So when it's negative, what you can expect? It hot, okay, right? The process becomes hot, okay, right? When it's positive, it cool down, right? Okay, right, guys, okay. If this is the is the formation of solids, right? Okay, so these will cancel that, right? So you will have LiCis plus 5, and then this already cancelled, right? So become minus 28,125 joules, okay, right? Okay, and also you can calculate also for the number of mole of solute, okay, right? Which is equivalent to number of mole of 2 over 1, okay, species 2 over species 1. You can use this equation here, right? Okay, for this, we want to produce right, the dissolutions of 1 mole of lithium chloride, 2 moles of water in the 8 mole of water, okay, right? So how are we going to do that? Okay, right. So this is the equation here, 2 and then 8, right, to produce this 10, okay, right? But since that we don't have it, so we can use this 10. Let's go back. Okay, 10, this equation here, minus 4,441,527,79. And then the formation of this, okay, this, right, 2 here, right, the formation of lithium chloride, and then the formation of water. Okay, water is not given here, but the formation of water is, okay, is 2 at 5, okay, right here. Okay, we can see here 2, this 2 cancel that, become 8, okay, right, so become 8 here, and then these 2, right, 2 is okay there, this cancel to that, okay, and this cancel that, so what we left is this minus this, become 8, okay, and that become, it's all cancelled already, so become 10, okay. So the heat of formation in the solute is minus 589 joules. Okay, right. So we can plot that it also here, the solute, you can see the number of mole per solute and then the enthalpy here. Okay, right. The higher number of mole, toward the end, you will get a flat graph here. Okay, right. So as it become pure, why is it? Okay, when it become toward this side, the more solute, it become toward the pure species. So will not produce any heat of mixing anymore because it's pure species. Right, so if you go further, right, the more dilution is that toward pure species, and this is finite dilution. Okay, okay, enthalpy contraction, concentration diagrams. Okay, right, guys, we can plot it here. H equal to H1 S1 plus H2 S2 plus delta H here, and then we can plot it into this concentration here according to the temperature, and then from this we can know how much water, mass of, I'm sorry, this for sulfuric acid and water, you know. So what is the percentage mass of sulfuric acid? Okay, it's 100%. You can see here it's almost toward neutral, right? Zero, right? Yeah, because it's pure species. But when the mixing here, let's say 50% at 0 degrees Celsius, that's how much heat of mixing you will encounter. Okay, the effect of mixing processes. Okay, right? Okay, right. So if you guys can see here, this is for pure species 2 and pure species 1. Okay, right? When it pure species will behave like a pure species. Okay, right? So this is the enthalpy for molar species 2, and this enthalpy for molar species 1. But when you mix something, you got this. Okay, right? So how to estimate this? And then we can use this equation here. Okay, right? With the solute. Okay, right? Okay, right? So we can find the what do you call it, slope. Yeah, the slope of this. Okay, right? So this is the value for H2 at this point here, H1 at this point here. Okay, Okay, other things also we can create it. Okay, right? So we can use either A and B and C. Okay, C is the mixing. A is for the separate species. Okay, right? And then we can rearrange this, and then we can get this equation here. Okay, right? And also we assume that like in this part here, it is a straight line. So we can write it into this form, h equal to mx1 plus k. Okay, right? So, and then we can cut into, it's the same thing. Okay, right? So it's curved, and then with this point here, then we can use the straight line. Okay, right? This for sodium oxide mixing with water. Okay, right? Okay, right. So that's it for the lecture. I know it's very short, but uh, you have to do your readings. Okay, right? If you want to read more, please read to your chapters. Okay, right? In the old books, 7 editions is chapter 12, or you can read Richard Elliott's and Lyra also, and chapter 10, activity modules. Okay, right? So all the best. If you have any question, please do not hesitate to talk to me. Okay, right? So thank you very much and have a good day and stay